Hey everyone, this is Derek, and this is going to be the first of 3 videos about polynomial functions. And so this one's about kind of a little bit of terminology and then some features of polynomials, particularly in behavior. And this video, like in and of itself, is kind of like, what just happened? Like, why do I care? You sort of need to see it with the other 2 videos that are coming. The next one sort of explains how this ties together. And then the third one is like an application that you can do with it. So first, a polynomial function has the form of that scary thing. And basically, this scary thing right here is just saying the coefficients, that's these numbers in front, are real numbers, so they're not imaginary. And then n, the power, the powers are going to be non-negative, so they can be 0. X to the 0 is a thing, that one's okay. And then they can't be fractions, because those are actually rationals, right? That's actually a root. So for a polynomial, it's our, x squared plus 3x plus 7. It's that kind of version that we've been seeing. A little bit of terminology. The degree of a polynomial is going to be the largest power. So it's not necessarily the one in front, because like this one isn't in the right order, but it's going to be the largest power. The leading coefficient is the a sub n, so it's the number or the value in front of the degree, the term with the degree of the largest power. Maximum number of zeros equals the degree of the polynomial. So if I have like an x cubed, that means the most I can have is 3 zeros. And then the maximum number of turning points equals n minus 1, or 1 less than the degree. So for this, and actually let me just say what a turning point is. For a cubic like this, that would be sort of what a cube might look like. And turning points are these places where the graph was going one direction, here it was increasing, now it's decreasing, so that's a turning point. And when you get to the calculus, this ends up being kind of what you end up caring about, because this is where something is maximized, this is where something is minimized, and those are interesting values. For this quarter, we're just figuring out that there can be 2 of them, and that's what this is stating. So for these first couple of questions, they're super easy. Find the degree and leading coefficients, and then maximum number of real zeros of the polynomial. Oop, and I didn't get max zeros down there. Oh well. So here the degree is 8, and so notice it's not in the right order. It's not in descending order, but that's okay. It's still 8. The leading coefficient is that negative 11, and the sign counts. And then it asks for the max number of real zeros, so that is also going to be 8 in terms of the zeros. And the reason for that is if I have an x cubed, I have to have an x times an x times some other x. There has to be 3 x's to get an x cubed, and each one of those can produce a 0. So that's why the degree and then the number of zeros is the same. For this one, so this one's already, it's factored. So to figure out the degree, what we do is we just count the powers. So right here I have an x cubed, and then if I FOIL that out, that would be x squared. And actually that would be 3x times 3x, that would be x cubed times 9x squared. So my leading term, I don't care about all the rest of it, but my leading term would be 9x to the 5th. So my degree is 5, that's our power, leading coefficient is 9, and then the number of zeros would have been 5, which matches the degree. Okay, so for this one, determine the least possible degree of the polynomial function shown. And so even though something is, say, x to the 16th, it doesn't mean it has 16 zeros. That would actually just have 1 zero. So when we're talking about the number of zeros, remember that's a maximum. So here they're saying what's the least possible degree, so that's just going to be 1 more than the number of turning points we see. So for this function, we have a turning point here and a turning point here. And so we have 2 turning points plus 1, so that would make it 3 would be the least possible. Here we have 1, 2, 3 turning points, so our degree would be, or least possible degree would be 4. Okay, so this is the page that, like, at least in terms of this video, it will seem like, why would we possibly care? And then this actually ends up being pretty good information and pretty easy to remember. So I would encourage you, even though it won't seem like a whole thing right now, it ends up being good. So there are, in terms of leading terms, there's kind of 2 things we were just talking about. We're talking about the leading coefficient, so some number out in front, and then some power. And so the number out in front, the coefficient, it could be positive or negative, and the power, it can be even or odd. And remember, we can't have negatives or fractions, so even or odd are pretty much what we got. And if we put those kind of two combinations together, that gives us four possible combinations: positive and negative, and even and odd. And so it turns out that everything that's an even power with a positive coefficient pretty much looks the same. It'll have a little bit different shape. They'll get steeper and then flatter right after one, for like this one. But they all kind of have the same shape in terms of going out to infinity. So for an even power with a positive constant, that would be something like x squared, so the parabola that we saw in the last section. And they're always going to look like this. So if I had something with, like, 17x to the 10th, that's positive, that's even, and long term, that's going to kind of end up looking like this function. So that's our even. And then even with a negative, that's going to be our upside down parabola. So this would be like a negative x squared is kind of what I think of for this. Odd powers, so that'd be like just y equals x would be the line like this, where it's always increasing. With this one, I have x cubed as the example. And then this one would be like negative x cubed. So if you can kind of remember what the two graphs are, and then the negatives are just the flipped over version, that helps you kind of keep track of all the signs. So let me show you what we do with this. So in terms of this video, it's just going to ask us to describe the long run behavior. Some books call it long run, some call it end behavior, a couple of different versions of this function. And we have a little bit of new notation. So this is the limit as x goes to negative infinity. So what we have is this function, and they're asking us, what does the function do as the x's go to the left? This thing is a negative, and it is even because that's to the fourth. And negative even things kind of look like negative x squared. So this thing would be opening down. So as the x's go to negative infinity, the y's, or the f of x's, the outputs, are going to negative infinity. And then the limit as x goes to infinity is also infinity. Or sorry, negative infinity. This next one describes the long run behavior of this. So here we need to, here we could just look at it and see what our leading term was going to be. Here we have to kind of add the powers. There's no negatives on the x's, so it's positive. And if we add them up, we got 1, 2, 3, and then that would be 4, 5 x's. So it's positive x to the fifth, and that would look kind of like an x cubed, which would be like this. So as x goes to negative infinity, the output goes to negative infinity. And here as x goes to positive infinity, then the output, the y values, are going to positive infinity. Okay, so then this page kind of gives us the other half of the stuff that we need to figure out what the graphs are going to do. So X-Intercepts Multiplicity. So first off, to find an X-intercept, we set the y to 0 and we solve. We've done that lots of times with polynomials, things like x squared minus 4 equals 0, and we factor and we solve that. The multiplicity is going to be the power that the zeros, the x minus the intercepts, are raised to. And then the sum of the multiplicities is the degree of the polynomial. So let me write this one out a little bit bigger. So here this is. So for this one, the zeros, it's the place where the x is 0, also the x-intercept, same thing. Here the 0 would be x equals negative 3. Here the 0 would be at x equals 2. This one we would say is multiplicity 4. So it's the number of times the 0 is repeated. And then this one we would say is multiplicity 5. And then what we're going to see is that for even multiplicities, like here, and it's not the term, it's not the value of the 0, it's the number of times it's repeating. So this is a negative number, but it's repeating an even number of times. And when we see that, what we're going to see is the function is going to bounce at that intercept. It's going to act kind of like an x squared. When we see an odd power, odd multiplicities, those are going to cross the same way x cubed or y equals x does. So behavior at the x-intercepts, that's kind of what I was just saying. If the multiplicity is just to the first, so if I have something like x plus 2, that would look kind of linear. It would just kind of cut through the intercept much like a line would. If I have something like here, this would be like x plus 2 squared. So that would act kind of like an x squared. And then this one where they kind of come up and it crosses, it's still crossing through, but it flattens out for a second. That tells you that you have something cubed. So that's kind of what we're going to see. For higher powers, like I was saying, everything that's positive and even is going to kind of look like x squared. Everything that's positive and odd is going to kind of look like x cubed. But we'll sort of be assuming these three. Okay, so this one is find the zeros and give the multiplicity of each. List the zeros in order from least to greatest. So here we have 0 at 4, and we're going to have 0 at -1. So it sounds like the computer is a little sensitive, so we'll do the -1 first, and we'll do the 4 second. So those would be my zeros, and then my multiplicity would be, that's a cube, so multiplicity 3 for the -1, and then 2 for the 4. This next one, same directions, but now we have to factor. Again, these questions are like, why are we doing this? And in the next video, you will see why we're doing this. So for this one, we just have to factor and do the same thing. So I will take a 4x squared out first, because that's my GCF. And I'm setting that equal to 0 because I'm looking for the zeros. Here we're going to go multiplies to -8 and adds to be 2, so that should be x plus 4 and x minus 2. So I'm going to have zeros at x equals -4, and there's nothing there, so that's multiplicity 1. And then at 0, whenever we have an x out front like that, that's just like 4x squared equals 0. Divide the 4 and root both sides, and x equals 0. And that's squared, so it'll be multiplicity 2, and then here at x equals 2, multiplicity 1.